SwayamPrabha. Digital India. Educated India.
Okay, welcome back. So in this particular lecture we are going to look at the entropy balance for various systems. So as we know that your delta S for an isoelectric system, that is change in entropy for an isoelectric system, is greater than or equal to 0. For the case of a reversible, of course delta change in the entropy is going to be 0, but for other cases it is always increasing. Thus your isolated system is said to be always increasing entropy, or in other word, for the case of a universe which we can consider to be an isolated system, the entropy keeps increasing all the time. So we can write this more formally, which we call as an increase in entropy principle. The change in the total entropy of the system is due to the total entropy or net entropy transfer from the surrounding plus the total energy generated due to any irreversibility. Okay, or in other word, we can write this as in minus S out plus any generation term. This will be the total entropy change of the system. Okay, and total entropy system is nothing but S2 minus S1, because this is a state function or the property of the system. Okay, in case the property of the system are not uniform, you make use of integral of the small volume or mass of the system, and you can write this expression as we have written for any other properties. Okay, so thus we can depict this entropy balance in the following form, that you have a system which is depicted in this form, and here your energy is shown as in and out, and as well as the entropy transfer in and as well as out, and thus there is a generation of entropy which is more than or equal to 0. Okay, thus you can write this in this form as was already mentioned. So this is entropy balance, and this would be your energy balance. Okay. So energy cannot be generated or created, thus you have a straight volume. There is no E generation term here. On the other hand, the entropy can be generated due to the irreversibility. So what are the mechanism of entropy transfer? So let us first look at it. There are two mechanisms, one due to the heat transfer, and the other mechanism is due to the mass transfer. So that will be for the case of open system. Okay. So let me just first look at the heat transfer. So as we already mentioned earlier, that the entropy transfer by heat can be written as in this form. Okay, or in other words, this is what we are assuming it to be reversible case. So S heat is nothing but can be written in terms of del Q by T, and for example, if this is a system and if there is a heat transfer from the surrounding, then this also can be approximated that various part, there is a small Qk coming from this different part of this boundary, and the corresponding temperature is Tk, and this can be approximated as the sum of all possible transfer in this way. Okay. We already mentioned that the entropy associated with the work interactions are 0. Okay. In other words, entropy is not transferred with work. So there is a entropy transfer due to the heat, and later we are going to talk about the particular case where mass flow can also transfer the entropy. So no entropy accompanies work as it crosses the system boundary, but entropy may be generated within the system as work is dissipated into less useful form of the energy. So when the work is transferred to the internal energy, that due to the dissipation into less useful form, this particular aspect can generate the entropy within the system. Okay, so let me look at the second aspect, that is mass flow. Entropy transfer due to the flow of mass in the control volume is nothing but simply m mass multiplied by entropy per unit mass corresponding to the flow, and this is simply the entropy due to the mass. Okay, and if the properties are not constant, that means they are changing during the process, then we make use of the definition as we have done for other properties during the discussion of control volume. So thus your mass contains entropy as well as energy, and thus mass flow in and out of the system is always accompanied by energy and entropy transfer. So now you can summarize this, the entropy generation, that you have S in and out, this is due to the entropy transfer by heat and mass, and then you have this S entropy generation. Okay, and that will be your delta S system. You can write this in terms of rate expression. Okay, and thus you can pictorially show in this form that S in is due to the mass, due to the heat. Okay, S out is of course also maybe due to the mass out and the heat transfer from the system to surrounding, and your delta S is greater than or less than 0. Okay. Now we can specifically look at a closed system, and later we are going to look at the control volume or open system. For the closed system, your mass contribution is 0. The entropy change is only due to the heat transfer or heat interaction. So the entropy change of a closed system during a process is equal to the sum of the net transfer through the system boundary by heat transfer and the entropy generated within the system boundary. Okay, in other words, this is entropy generated due to the heat interaction plus the generation term, that would be the change in the entropy of the system. For the case of adiabatic closed system, that means your Q's are 0, your S generation is simply delta S system. So any closed system plus the surrounding can be considered adiabatic. Okay, so that means you can consider any differential change from the system boundary to the surrounding where the temperature, there is a temperature gradient, and you can consider completely your surrounding as well to make it an adiabatic. In that case, you can write S generation nothing but, as we already mentioned earlier, that this can be written as the sum of all subsystem, that can be written as now delta S system plus surrounding. Okay, that will be the S generation of this particular combined closed system or the system plus surrounding. Delta S system is nothing but your mass time the change in the entropy in per unit mass unit. Okay, thus, and as well as the entropy change of the surrounding can be written as simply your delta S surrounding is equal to Q surrounding by T surrounding, considering T is to be constant. Okay, so this is the simple expression of your entropy generation. So you can plug this information to obtain the S generation of the system plus surrounding. Okay, so for the case of control volume, you have to also consider due to the transfer, due to the heat, entropy transfer due to the heat, and as well as entropy transfer due to the mass. Okay, so that will be in addition to the entropy transfer by heat. So you have to also include the mass contribution as well as the heat contribution. So thus you can write this expression of the control volume, the change in the entropy of the control volume, okay, which is here, as due to the heat interaction and due to the mass interaction, that means your inlet minus outlet plus the generation. Okay, you can write this expression in terms of rate. For the case of steady flow, your this dSCV by dt is going to be 0, and thus your S generation can be written as your exit entropy due to mass minus inlet minus the heat contribution or the entropy due to the heat interaction. For the case of a single stream, you can write this much simpler expression. Okay, you can take one single and this is can be written as this, and if it is a adiabatic, that means this expression is 0. So this is 0 for adiabatic, and thus your S generation is simply entropy of the exit stream minus the entropy of the inlet stream. That will be S generation. Okay, so that is the way to look into this aspect of entropy. So thus from this analysis, so entropy of the substance always increase or remain constant in the case of a reversible process as it flows through a single stream adiabatic steady flow. So this tells you that entropy is going to be greater than or equal to 0, which essentially means that your SE is going to be greater than or equal to SI, okay, for a steady state single process. So this is your control volume. Now we can do simple examples. So let us look at entropy balance for a heat transfer through a wall. Now we can write down the entropy general balance here, entropy transfer by heat, and this is your generation. There is no mass aspect here. Okay, so we will look at the entropy due to the heat transfer. There are two aspects here. So one is inlet and this another is outlet. So inlet is at so that is your in and this is your out. There is no mass contribution here. Okay, and this is nothing but the temperature at inlet and this is at temperature outlet, which is in this case, if you consider this to be a system here, your temperature is at this boundary. Okay, so this boundary temperature is 20 and this boundary temperature is 5 degree Celsius. Okay, and thus you will be considering Q, which is going to be same, and temperature here would be 20 plus 273 and here is going to be 5 degree Celsius plus 273. You can also apply similar exercise to a throttling process. Okay, so this is a throttling process and you have to find again the S generation. Okay, remember this in the previous one we've considered this to be a steady state and hence your dS system by dt is 0. So in this throttling process the pressure and temperature for the inlet is given and the outlet is P2. Okay. Now we know that your enthalpy is going to be constant for the throttling process. Okay. So we can calculate here your H and S, and here of course this is going to be S2 is equal to H1. So based on that you can find out S2 from the table. Okay. Now you can look at this entropy balance here. This here there is assuming to be adiabatic. So there is no contribution due to the heat transfer. The contribution is mainly due to the mass flow. So this can be written as MS1 minus MS2 because mass m dot is fixed considering single stream steady flow system. Thus you can write U as generation in this form. From this analysis you can find out S1, and from the conditions of P2 is equal to 3 megapascal and H is constant, you can find out S2, and thus you can calculate S generation for this throttling process. Okay. So let me end this lecture with this example. So this is an example of a frictionless piston cylinder which contains a saturated liquid vapor mixture of water at 100 degrees Celsius, and during a constant pressure process 600 kilojoules is transferred to the surrounding at 25 degrees Celsius. As a result, part of the water vapor contained in the cylinder condenses, okay, because you have taken out the heat from the system. And what we have to find out is entropy change of the water. That is the first question, which becomes very simple if you consider this to be your system. So this is your system, okay, and what we are going to consider that there is no irreversibility within the system, and thus you can clearly write your delta S system is due to the heat interaction, okay, and which will be simply your Q divided by T of system. Okay. So this we are going to consider based on internal reversibility. Okay. Now in order to find out the total entropy generated, we will be considering slightly the region outside the system, which will include the immediate surrounding where the irreversibility is associated with, and where you have the temperature gradient for that matter, okay, because of the temperature gradient from 100 degrees Celsius and outside is 25. So irreversibility is associated within here. Okay, and thus when you are considering this extended system which includes the system plus immediate surrounding, this entropy balance can be written in this way, which is a general entropy balance, and here you will be considering Q out because Sn is 0, the Q out is due to the heat transfer, will be at Q out at the boundary plus the generation which terms within this particular extended system. So this is the same term which we have used earlier. The only difference is in terms of T. Okay, T is at the boundary. So earlier what we have done is when we calculate the system we have considered the T as for the system, but now here when we consider the extended system we are considering the boundary temperature at which your T is 25 degrees Celsius. We are assuming this temperature here is also at the boundary is 25 degrees Celsius. Okay, this expression is nothing but 600 kilojoules divided by 25 degrees Celsius, that means 25 plus 273. Okay. So with this rearrangement you can calculate S generation, which will be this term plus your delta S of the system, which we have already calculated earlier, and thus your final expression is this. So the key to solve this problem is clearly that the assumption which we have made, that internal reversibility for the system, and by considering the extended system plus surrounding we included the entropy associated with the outside the system, that is around the boundary between the system and the surrounding. Okay, that means the region where the temperature gradient is there. This is a kind of an example where you can take this message and apply to the other kind of systems. So we will be ending this particular lecture now with this, and we will try to summarize what we have gone through this particular module. So we have looked into the definition of entropy, understand the increase of entropy principle, which means entropy is generated and all the time it increase, if not remain constant. We made remarks of entropy in terms of what are the reasons for irreversibility. Okay, we talked about entropy change of pure substances and the asentropic process where entropy is constant. Property diagram such as HFS where it becomes very useful to describe the process where the entropy is involved. Okay, we also looked into the molecular behavior of entropy, the relations such as TDS in terms of internal energy or changes or the enthalpy changes, entropy change for liquid and solid we have looked into, and particularly for the ideal gas. And once we looked into the ideal gas we also derived the reversible steady flow work, and specifically how to minimize the compressor work by considering intercooling in the middle stage of the compression. And in the end we compare the efficiency of the steady flow devices by defining isentropy efficiency. And in this particular lecture, we looked into the entropy balance, derived the expression, or demonstrated how to calculate the S generation of a particular processes. Okay. So, with that we will end this particular lecture, and in the next lecture we are going to take up another topic. Okay. So, I will see you in the next lecture.